All right, good morning, topology class. It's the last video lecture. Kind of sad, actually, but let's go ahead and knock it out. So we're going to call a property of a topological space a topological property if any other space that's homeomorphic to the space with this property also has the property. Does that make sense? So here I'm saying, look, if our space XF has a certain property, P, let's call it, and any other space that's homeomorphic to XF also has property P, then we're going to call P a topological property. And so an example / theorem is that the property of being Hausdorff is in fact a topological property. And so let's set up the proof, and then we'll actually work through it together. So we're going to go and suppose that a space, let's say XF, is Hausdorff, and then we're going to pick any other space, YR, that's homeomorphic to XF. And so since we're claiming that Hausdorff is a topological property, then that means that YR should also be Hausdorff. So we need to show that YR is indeed a Hausdorff space. So let's work through this. So I thought it might be good to remind you of what a Hausdorff space is. So I've gone ahead and written down the definition that we're going to use in red. So this would not be part of my proof typically, but this is what you do when you're working on something. Maybe you don't know the theory as well as you would like. Well, then you'd want to go back, either thumb back and look at the definition, or even write it down. A lot of times I'll keep a kind of a running list of all the key facts or definitions that I need. So we know that the space YR is Hausdorff if and only if for every pair of distinct points in Y, you can find open sets, U and V, where Y1 is in U, Y2 is in V, but the intersection is empty. So the idea is there's a separation. You pick a point here, you pick a point here, and you can put an open set around Y1 and an open set around Y2 where the intersection between them there is no intersection between them. These open sets don't overlap. So that's the idea. So what are we going to do? Well, from the definition, we can kind of see the next step in the proof. We can say, all right, let's go ahead and choose our 2 points. So let's choose Y1 and Y2 in our set Y, and we should go ahead and say with Y1 not equal to Y2. All right, so now let's stop and think about what are we assuming. We're assuming that X is homeomorphic to Y. So let's write down what that means. So we can say by assumption, there exists a bijection, let's call it H, from X to Y, such that both H and H inverse are continuous. And that means that for both of these functions, their preimage of an open set is open. Okay, so now let's think about it. First off, we're interested in the fact that I'm picking these points in Y that are distinct. These are distinct points, and I want to look at what happens back in X. So remember, we're thinking of, let me switch to pink. We're thinking of H going from X to Y. I picked 2 points here in Y, and I want to look back now over here in X. There's a bijection between these sets, and so in particular, the fact that H is 1-to-1 tells me that H inverse of Y1 can't equal H inverse of Y2. So let's write that down. So since H is 1-to-1, H inverse of Y1 can't equal H inverse of Y2. And I am saying inverse here, not preimage. But in particular, if you were thinking preimage, the preimage of, when there's a bijection, the preimage of one thing here will be one thing over there. So the preimage and the inverse agree in this case. Okay, so now we say, wait a minute, okay, where do these live? These 2 points, these distinct points actually live here in X. And so, wait a minute, we know that X F is Hausdorff. Let's go ahead and say that. So we can say, but X F is a Hausdorff space. So we know there exist open sets. I'm going to be redundant and I'm going to say U, V, in F. I already said they were open, but let's go ahead and just say that. Such that what? Well, we know that, let's say H inverse of Y1, that's an element. You could label it X1 if you want. I'm just going to leave it H inverse of Y1. This lives in U, and we know that H inverse of Y2, this is a singleton element here. You could label it X2 if you wanted. I'm just going to leave it like that. This lives in V, and even more importantly, we know that since XF is Hausdorff, U intersect V is empty. And so somehow we want to take that, what's happening here in X, and translate it back to Y. Well, let's think about it. So we can say, look, since H is a homeomorphism, then we know that H and H inverse are open functions. And we talked about this briefly in the last lecture. I don't remember if I assigned it as a homework or not, but you can look at exercise 11 in 3.3, and it tells you that anytime you've got a homeomorphism, then it and its inverse are actually both open functions and closed functions. All that means is H and H inverse carry open sets to open sets and closed sets to closed sets. So we're going to use that here regardless. And like I said, my reference for that fact is exercise 11, 3.3. Let's actually write that down. C, exercise 11, section 3.3. Okay. So they're open functions. So what does that mean? So we can say thus, well, let's realize that, I'll switch pages here, H of U and H of V are open. These are open, i.e. they live in R, right? H of U and H of V both live in R. Again, being redundant, but just trying to be clear. So just to show you what we did, we started with these sets UV. These are open sets in F. And then we said, well, wait a minute. We know that we have this nice continuous function H, which maps me from X to Y. And when I plug in open sets into homeomorphism, I get out open sets. And so these are open sets. You can relabel if you want to, but I'm pretty happy working with H of U and H of V. These are just open sets, and they live in R. And so now I'm going to say, wait a minute. Let's say also, note that Y1 is certainly H inverse of Y1. Where did H inverse of Y1 live? H inverse of Y1 lives in U. So H of H inverse of Y1, which is just Y1 by the way, certainly lives in H of U. And you can check that Y2, which is H of H inverse of Y2, certainly lives in H of V. Okay, so we've actually been able to do two things. We've been able to take our 2 points. We picked Y1, we picked Y2. We've got open sets around them. The open set around Y1 is actually H of U, and the open set around Y2 is H of V. And so now we need to show that there is no intersection. I went ahead and drew my picture like there was, but the point is we want these to have no intersection. So let's erase the little picture, and then we will go ahead and check that. So let's actually say it remains to show that what H of U intersect H of V is actually empty. So let's prove that. So we're going to go ahead and say, look, assume for a contradiction that the intersection isn't empty, that H of U intersect H of V is not empty. What does that mean? Well, that means then there exists some Y in H of U intersect H of V. It's in both of them, right? It's in the intersection. And so, well, let's think about it. So thus, H inverse of Y is going to be in the preimage of H of U under H inverse. Actually, you know what? No, not preimage, I'm sorry. It's going to be in the image of H of U under H inverse. No preimage here. It's the same, actually, but this is just U. And in fact, we can also see that H inverse of Y is going to be in H inverse of H of V, which is just V. And so wait a minute, that's a problem. This element is in U and this element is in V. And so that means that H inverse of Y is in U intersect V. But wait a minute, U intersect V is empty. That's because it's Hausdorff. We said that at the beginning. So this is a, let's say, which is a contradiction. Okay, so we can say thus, actually, H of U intersect H of V is empty, and it follows that YR is a Hausdorff space. And so that's the proof, and what it's saying is, again, if U being a topological space, are a Hausdorff space, then anything else that you are homeomorphic to is also a Hausdorff space. And it means that if you find another space that isn't Hausdorff, then you can't be homeomorphic to it because it's not Hausdorff. So that's just an example of a topological property. And that is sort of the big bridge between the material that we looked at on our quote-unquote fun day. We talked about how a coffee cup is sort of the same as a donut from a topological viewpoint. Well, there's a homeomorphism going on and continuous deformations. And anyway, I won't get into that, but that's where you can go from here. I wanted to end with just two definitions, a little fact, and then I'm going to leave you guys with a brief homework assignment. So let's look at these definitions. I went and wrote them down just to save time. Pick a topological space. Pick a subset of your space, let's say A. We're going to call A dense if the closure of A gives you the whole set. That's a really important idea throughout mathematics, so I wanted you to see that. And then we're going to call a space separable if it has a countably dense subset. And it turns out I'm not going to prove it with you. You can see the book. It's in the section 3.5, but separability is a topological property. So it's like Hausdorff, if U as a topological space are separable, then so is any space that you're homeomorphic to. So, all right, let me make a few comments on the homework. 12 and 13 are kind of not terribly long problems. They're just asking you about the reals under different topologies and this idea of being separable. So that's 12 and 13. Number 1 is just a generalization. It's a little bit broader idea of Hausdorff. So we're going to get into what's called a T1 space. So we said Hausdorff is the same thing as being a T2 space, and I wanted you to see what a T1 space is. And so you're a Hausdorff space if you can take 2 points, any 2 distinct points, and you can find open sets around them that actually don't intersect. You're a T1 space if you take any 2 points and you can find open sets around them where the open sets themselves might intersect, but this point is not in the open set around this point, and vice versa. So they still have space. In other words, the point that you pick is not in the intersection. Neither point is in the intersection here. So I wanted you guys to play around with one more definition and proof. I'll just mention problem 1. The proof should work out pretty similarly to the way that I proved Hausdorff. There was a similar problem for Hausdorff spaces. We proved that in a Hausdorff space, any finite set of points is closed. It's actually very much related to being a T1 space as well. And we looked at 2 proofs. One of the proofs I had you guys think about the boundary But then if you look at the solutions I posted, I worked out one without that as well. And so I would encourage you guys to look at that and see if you can prove number one, just to get you started. Well, yeah, you know what? I'm not going to get you started, but if you would like, we can chat about it this week. I'm going to ask you to have these due by Friday, but if you guys want to meet on Wednesday as a class briefly at class time, I'd be happy to do that. So see what you can do, and then we'll go from there. All right, well, that's more or less a semester. It's been a lot of fun. I know I've got some grading to do. I'll get that done, and going to give you guys some kind of a take-home final project. Not going to be crazy long because I don't think any of us want to spend all week for you working out something long, or for me having to create and grade something crazy long. But I do want to give you a project that will help you learn, kind of one last learning exercise. So just be watching your email or Teams for information on that.